Welcome to podcast number 91, and today we're talking about the Lattice Boltzmann method and using it to simulate the high-speed noise from high-speed trains, noise from high-speed trains, and this is coming from the pantograph. And we've done noise of high-speed trains in podcast number 22 and 23, but that was actually using not the Lattice Boltzmann method. So we want to look here if the LBM can do it in terms of CFD. And I've done other podcasts on the Lattice Boltzmann method recently, seeing how this fares in terms of its accuracy compared to experiments and other CFD methods and Navier-Stokes methods. So if you want to look at them, you can find them in other podcasts recently. And so let's continue here. So this is going to be a two-part podcast as well because there's a lot to cover. We're going to be covering some of the mechanics of the Lattice Boltzmann method for CFD, plus the validation effectively of it for these high-speed train noises. So we're going to be looking at a paper called Numerical Analysis of Aerodynamic Noise from Pantograph in High-Speed Trains using Lattice Boltzmann Method. So the pantograph is if you look at a regular train and you look at the top, the stick coming up and hitting the electrical cable, that's the pantograph, that entire structure. And that gets electricity and comes down to the train. And in podcasts number 22 and 23, we saw that the pantograph accounts for a lot of the noise that a high-speed train does make. And that's because there are all these little bits and pieces around that create a lot of turbulence, and its unsteadiness as well, that results in not only tonal noise, but also broadband noise. So we looked at how to reduce that noise there as well. But we're going to look at this paper here, which looks at the LBM mimicking the noise being produced and how it's being produced. So let's get into it. And this paper is open access, by the way. You can find it in the link in the description. And so let's start now. The aerodynamic noise of high-speed trains increases sharply as at a running speed over approximately 300 kilometers per hour. The primary sources of aerodynamic noise are the front nose, the pantograph, the intercoach spacings, and so on. So in podcast number 22 and 23, we found the nose, also the near the wheels, whether they had fairings or not, and then the spacing between the two carriages, as I mentioned, and the pantograph, but also the structure around the pantograph. So if you have like a little like air conditioning unit or something, that does change the noise coming from the pantograph. They say among these, the pantograph is composed of protruding shapes in contact with the cantery for power supply. Therefore, high air resistance and complex flow of the pantograph are inevitable at high speeds. The beamforming method was used to measure and analyze the propagation of noise of the pantograph using a microphone array in other setups. So in other experiments, they use something called a beamforming array. And this I'm a big fan of, mainly because I actually have a friend who did a lot of work in terms of developing a beamforming method, and it's really cool. In other words, what it is, you have a bunch of microphones around your structure. It's usually in a two-dimensional plane, and then you can determine where the noise is coming from based on how long the differences in time that the noise is picked up for the different microphones. So the changes in the phase between the waves, but also if you have a noise being emitted at a certain time, because the microphones will be picking up at different points along the time spectrum because they're different distances away from the noise being propagated. You can triangulate where the noise is very accurately, and you can see how the noise is evolving over time. It's very powerful and it's really cool. So they say, however, it is difficult to obtain the aerodynamic noise generation mechanism through measurements performed using microphone arrays. Conducting numerical analysis by employing computational approaches is useful for deriving the noise generation mechanism of the pantograph. So that's true to some extent, depending on whether the CFD is very well defined and has a high resolution or not. It can be better than beamforming, and that goes for pretty much every experimental method. If your CFD is very good, then you can overtake your experimental method in terms of the data you get out. But that's only if the CFD is actually accurate, which is actually part of the thing we're going to be looking at with these two podcasts coming. So they say, in recent years, two-stage hybrid methods based on CFD and computational acoustics have been developed for investigating the noise generation mechanism in high-speed trains. So one thing we should talk about is that traditional CFD, so using Navier-Stokes equations, particularly URANs and even DES and even LES to some extent, they're not very good at predicting the aeroacoustic behavior of objects. So for URANs, for example, there is so much simplification, and the boundary granular equations that you use are so empirical and heavily simplified that the information that you need to predict noise and to model noise is completely, not completely lost, but very obfuscated. Like it's very little information left. So trying to get accurate noise generation and propagation from these CFD methods is challenging at the best of times. Then you put in something like a pantograph, which is very nuanced, and there are a lot of different structures coming off of it. It becomes very inaccurate if you use URANs. So alternatively, they say that the aerodynamic and aeroacoustic behavior of the flow past a simplified high-speed train bogie at a scale of 1 to 10 was studied at a flow speed of 30 meters per second. In particular, near-field unsteady flow was obtained by numerically solving the Navier-Stokes equations using the delayed eddy model, so the detached delayed eddy simulation, so DES or DEDES or IDDES. I'm not sure which one they're referring to here, but it could be any of those. They say, and the results were used to predict far-field noise using the Fox-Williams-Hawkins method. So this is just another equation that they plug in the information you get from a typical URANS, or in this case, DES simulation, and you get the noise. They say a dipole shape was observed for the noise radiated from the bogie, and the noise contributed from the bogie frame was relatively weak compared to that from the wheel sets of the bogie. So the bogie is just the carriage. But some things we should talk about here. First of all, they say the dipole shape. So noise can propagate in a bunch of different ways. It can be in a dipole shape, which looks like an infinity sign. If you just look at an infinity sign, that's how noise propagates from an object. It could be a quadrupole, which means that you have two infinity signs, one horizontally, one vertically, and they propagate in that direction. Then you can have octopoles, which are then you have three infinity shapes in all orthogonal directions. Traditionally and notoriously, CFD does not pick up octopoles very well, and even quadrupoles not so well. So dipoles, URANS is okay at, and but to get quadrupoles and octopoles is terrible at. You then go to DES and then LES and so on if you want to get these more delicate sources of noise. They say, however, while hybrid simulations might be able to capture the global characteristics of a small-scaled system in a few cases, it does not allow for the prediction of the actual highly unsteady flow field present in the system during operational speeds, and can lead to large errors in the prediction of propagation noise depending on the flow conditions and geometry of the system. So why is that? Well, in this particular case, they're looking at DES, and DES is a combination of LES and RANS. So how DES works is that depending on where you are in your simulation, you're going to be triggering either LES or RANS equations. In effect, when you're close to the wall, you're going to be triggering the RANS equations. So that's problematic because that's where sound is really a lot of it's being produced. So if you're using turbulence modeling, you're losing a lot of information, or you're not even getting the information to begin with the RANS equations. So that's why DES can struggle in this particular case. Going to LES is better, but then you again have fine scale things, information which you're not modeling or simulating. And so you need to go even finer grids and, trending towards DNS to get good sound with very delicate systems. So furthermore, the method is expensive in terms of computing power, owing to the large meshes required for simulating the propagation of the acoustic fields. That's what I was mentioning, where to get these fine and detailed structures of noise, you need to have a very fine grid, a very high grid resolution. They say, however, in the past few decades, a CFD method referred to as the Lattice Boltzmann Method, or LBM, has been developed. The LBM implemented in the commercial solver PowerFlow provided a satisfactory combination of reliability, simulation time, and usage flexibility in this application. So PowerFlow, it wasn't the first commercial solver from my knowledge, but it definitely, from my experience, is the most widespread commercial solver for the Lattice Boltzmann method. So, despite the advantages of the LBM, there have been no studies on applying the LBM to predict the noise generation from high-speed trains. In this study, the aerodynamic and acoustic performances of a pantograph in a high-speed train were investigated through numerical analysis using the LBM. First, a real scale pantograph was modeled using CAD, then the surface and volume measures of the pantograph model were generated for simulation analysis. So let me just quickly talk about this here and the difference between LBM and Navier-Stokes. So they said surface and volume measures. So the surface measure is when you have the object and then you are meshing it so that the CFD can recognize the surface. That's the surface mesh. Then the volume mesh is the cells that you actually have in the volume. So the surface mesh is two-dimensional cells. The volume mesh is three-dimensional cells. Unless you have 2D simulations, of course, in which case the volume mesh is 2D as well. But I digress there. In which case, I guess that the surface mesh would then be 1D cells. Oh no, it'd still be 2D, but that have only no area. Now, for the Lattice Boltzmann method, you do the same thing, but they're called different things. They're called surflets and voxels. And the voxels are effectively the equivalent of a Navier-Stokes CFD cell. I just want to touch upon that there. Okay, so the numerical simulations were conducted at speeds of 300 kilometers per hour based on the Lattice Boltzmann method, and this is what they mentioned later, the speed of the high-speed trains in South Korea. So what is the Lattice Boltzmann method? They say that the Lattice Boltzmann method is a different kind of CFD tool compared to the classical CFD methods, such as Reynolds average Navier-Stokes, large eddy simulation, and direct numerical simulation. So these are all Navier-Stokes based CFD approaches: RANS, URANS, DES, DDES, IDDES, LES, DNS. And they say it does not depend on the discretization of the Navier-Stokes equations, but rather on the statistical distribution of particles in a given fluid and their interaction based on the Lattice Boltzmann equation, which is derived from the original equation proposed by Boltzmann in 1872. So in other words, I covered this in the other podcast that we looked at Lattice Boltzmann method, but I'll just briefly talk about it here. With the Navier-Stokes equations, what they were saying here is you look at a macroscopic point of view, the fluid, what it's doing at each point in the space. But for the Lattice Boltzmann method, you look at individual points in space and you say, okay, this point is representative of these particles in this area. And we assume a certain a density, like a distribution of particles in this area as well. And then we calculate the properties from this angle. And we use the Boltzmann equations. They say this LBM highlights a fundamentally different approach to the resolution of flow fields because the primary flow features, such as density, velocity, and pressure, are not resolved directly. Instead, the layout is determined and the evolution of the individual particles of the fluid is calculated from which macroscopic properties can be obtained. So this is a very different approach for CFD Navier-Stokes compared to Lattice Boltzmann. So Navier-Stokes, you are calculating the density, the pressure, and the velocities straight up. The Lattice Boltzmann method, you're calculating the velocity of these particles, and then from there, you're indirectly calculating the density and the pressures, and whatever else you want. We'll cover later that there is more information that the Lattice Boltzmann method does contain compared to the Navier-Stokes equations. So, briefly, I just want to talk about something called streaming and collision. So these are the two main steps in the Lattice Boltzmann CFD process, and they are important because the streaming is where the information is coming into one node, and then the collision is this information and these particles traveling in their final destination effectively after the streaming phase. And this is important because they say the Lattice Boltzmann method analyzes flows in the Boltzmann equation as the governing equation, which defines the behavior of particles, including movement and collision, in a discretized lattice as a probability distribution function. The Bartnagar-Gross-Krug method, the model, BGK in other words, with a single relaxation time with the D3Q19 model, which uses square grids in three-dimensional space, are widely employed because the collision term of the Boltzmann equation is considered. So let's talk about all this. There's a lot of different terms coming in here. So I mentioned the collision side of the simulation. They're saying these particles, how they're colliding and moving after that, so the distribution, the probability distribution after that. They say something called the Bartnagar-Gross-Krug model. And this is just effectively the, I'm not sure if you call it the gold standard, but is the most common model used for the collision equations. It's just their way of processing of calculating this collision process. They say with single relaxation time. So this is important because single relaxation time and multiple relaxation times are different. Single relaxation time means that you're using only one relaxation time for all the properties that you're calculating, whereas multiple relaxation time means you're using different relaxation times for different properties. And the benefit of the multiple relaxation time is that it increases the stability of the CFD simulation. The difficulty with it is that it's still being developed because it's a little bit unintuitive. Like when you first do your simulations, it takes like you have to do some fancy maths to figure in the different relaxation times. So they're using single relaxation time here, so all the properties are calculated with just one relaxation time. And they say the D3Q19 model. So I have a picture here on the video, and if you can't see the video, you can see it either on Spotify or our YouTube channel. And the image is a cube, and in the middle you have 1 point. Then you have around the cube you have all these different points, 18 to be exact. And this is called the D3Q19 model. What this means is for every point you have 18 other points that are connected to this point in terms of information being transferred. And so in total we have a 19-point system for each point that you're looking at. And this is for 3 dimensions, D3, 3 dimensions, Q19. Now you can have a bunch of different models. You can have D3Q27, or you can have, like, for example, D2Q9, which is only for 2 dimensions. And the benefits of these different models are increased accuracy and stability depending on your simulation. So what this means is that the point in question has information coming from 18 different points around it into it, and then the collision equations have these points moving however they should be afterwards. And if you have a D2Q9 method, it means that there's only 8 other points that are connected to the central point. So that's what this D3Q19 means. So they say that they have the schematic here of this setup here, and it's quite intuitive. These points are effectively spaced kind of equidistantly around the original point, but not really. It's more equiangular more than equidistant when you think about it. There, when you look at the angles, they're all angularly spaced. So, moreover, the LBM recovers the compressible Navier-Stokes equation and the acoustic flow properties of a given solution. This is very different to the Navier-Stokes equations when we use them in URANs or the DES phase or whatever. Therefore, because of this acoustic flow properties that it also recovers, the direct acoustic simulation becomes feasible. That's a major benefit that it has over Navier-Stokes CFD. Therefore, the Lattice Boltzmann method is of interest for investigating acoustic sources for a given application, as it allows for the simultaneous evolution of aerodynamic phenomena and their acoustic effects on a given flow through direct simulation. And this is why I wanted to look at the Lattice Boltzmann method for acoustic modeling, because acoustic modeling in traditional CFD is incredibly difficult and very erroneous. So the Lattice Boltzmann method may provide a different way of doing that, of getting this acoustic modeling accurately. So let's talk about the verification of the computational method. So they say, the aerodynamic and acoustic analyses were carried out for basic shapes to begin with, such as a square and a circular cylinder. Based on the Lattice Boltzmann method, the shape and the drag coefficient, the Struhl number, and the sound pressure levels were derived using computational simulations. So they say here, the square length was 0.019 meters, and the free stream Mach number was 0.2, which corresponds to a Reynolds number of 90,000. A structured form mesh with the finest voxel size of 0.2375 millimeters was employed. So this is important because currently pretty much all Lattice Boltzmann methods, maybe not PowerFlow. I'm not too familiar with PowerFlow, but every other Lattice Boltzmann method that I've come across, the software, uses structured meshes because an artifact of the simple approach to implementing the Lattice Boltzmann method is you need to have the each point equispaced from each other. So you get a structured mesh. And they say here the finest voxel size was 0.2375. So this is, again, the voxel size to the cell size, the equivalent. In figures 4 and 5, the drag and lift coefficients were calculated for the square shape, and the drag coefficient is 2.21. The Schur number is 0.14. The measured results are similar to those of Orselli and others, so other researchers. They found a drag coefficient of 2.20, so it's almost identical to 2.21 found here. The Schur number that they found was 0.12 instead of 0.14, so that differs a little bit. The characteristics of the noise generated in the flow of the square-shaped model are shown in figure 5, so let's have a look at that. So these show the tonal noises and the frequency being calculated from this CFD simulation. They say the analysis of the generated noise shows that the sound pressure level or the fundamental frequency corresponds to the Schur number is continuously generated by harmonics. That makes sense. There should be that, where you have the fundamental frequency, which here is about 600 or so, and then you have harmonics from there. Harmonics are multiples of that number. So it could be 600, 1200, 1800, 2400, so on. And it's good that they're calculating these here. They're finding them. In figure 6, they have the Z vorticity or Z vorticity around the square, and they say that it predicts this LBM CFD predicts the periodic vortex shedding around the square here, so that's very good. We should be seeing that too. So generally speaking, this CFD approach is giving quite good results. It's agreeing with literature, so that's always nice. So they say the numerical analysis of the pantograph now. Let's look at this. They say the finest voxel size used was 0.5 millimeters with a maximum voxel size of 8 millimeters. So this resulted in a mesh of 27 million voxels in total and 3 million surface meshes or surflets or circles, depending on the program that you're using. They use different terminologies. So here I should point out the software that they used have different voxel sizes, and this is because of PowerFlow. So here they do show that PowerFlow, you can use different voxel sizes, which is a massive advantage. It means that you can use fewer voxels in the entire domain and still get an accurate simulation, whereas other softwares, including open source ones, currently they don't usually allow you to have different voxel sizes. So that means if you want to have an object highly resolved, then the entire domain has to be highly resolved too. So you get a lot of voxels that you don't need. But unfortunately, that's an artifact of the equations, the simple equations. So they said temporal resolution in the simulation based on the finest voxel resolution was 9.18 by 10 to the minus 6. So this is important because the temporal resolution is linked to the voxel size, where the smaller the voxel size you have, the smaller the temporal resolution has to be. And this is kind of akin to the Courant number in Navier-Stokes CFD. The Courant number is the finer the mesh you have, the lower the time step you need to have, because if you have too high a time step, then effectively particles are traveling through too many cells between time steps. So you then start not being able to model the flow properly. So that's why you need to have a low Courant number. Below 1 is ideal. Below 5 is good. Below 1 is ideal. And the same kind of idea happens here, where you need to just have a lower temporal resolution, or a finer temporal resolution with a finer mesh. So the frequency range of the analysis was up to 3,000 hertz. So I wanted to cover this as well, because this is an important point. They say that, and the time step was selected by considering the aliasing effect. So what is the aliasing effect? This is something that comes into play with aeroacoustics, but also sampling in general, digital sampling. So what this is so with acoustics, for example, let's say you have a frequency of 100 hertz. So that means every 100th of a second, you have an entire wave being completed for this frequency. So to sample this properly, the sampling law is you need to have at least twice the sampling frequency of this frequency, because if you don't, then you won't pick up the frequency properly. What will happen is you will start registering this frequency as being not 100 hertz, and it will come up as different hertz. And it'll be pretty much noise to some extent. So to measure the this frequency accurately, you need to have at least 200 hertz. So what they're saying here is the frequency range of the analysis was 3,000 hertz. They're considering all noise up to 3,000 hertz. So to consider these frequencies, they need to be sampling at least 6,000 hertz, at least, and this will stop the aliasing effect. Now, with the aliasing effect with this particular case, I think you need to know kind of in advance what the highest tonal noise will be to be able to make that call definitively. However, if you know any more about this, let me know in the comments below. I'll be interested to find out. So they move on and talk about figure 14 and figure 15. So the noise generated from the pantograph is closely related to the time derivative of the pressure in the flow field. In this sense, large pressure fluctuations occurred at the locations of the panhead, joint, and base sections, as shown in figure 14. So in other words, when you get a lot of turbulence, a lot of fluctuations in pressure, then you get a lot of noise. And if these fluctuations are consistent, so they're periodic, then you get a tonal noise. If they're not, then you get a broadband noise. And what they're saying here is various parts of this pantograph are producing noise, including the panhead joint, so the panhead, the joint, and the base section. Moreover, it can be seen that complex turbulent flows were generated through the panhead, joint, and base section, which makes sense. This is where the acoustics is coming from. In particular, complicated vortices were observed in the collector head, slide, plate, and guide horn of the pantograph, as shown in figure 15. So in other words, the strips that go along the wires, like, you know, if you look at a train and you have this wire popping up from the train, on the top they have like these long strips. These strips are, they're metal and they are producing a lot of turbulence. Also, the little U shape of metal that's connecting these strips to the main bar that goes down to the train is also producing a little bit of turbulence as well, and this is where noise is coming from. So moving on to figure 17, they show how the noise is propagating in different directions, and this is what I was talking about earlier with dipoles, quadrupoles, and octopoles. They say the sound pressure level in the propagation noise from the panhead section range from 102.3 decibels to 107.6 decibels, and this is A-weighted. So A-weighted decibels is the based on human hearing. So humans don't actually register the same intensity of noise across the spectrum. If you have a noise at 100 hertz, for example, 100 decibel 100 hertz noise might be the equivalent of 102 decibels at 5,000 hertz. I don't know exactly, but this is just a general idea of how the decibel with A weighting works. So they're A-weighting it for human hearing. And what they show here is the sound pressure level propagating from the panhead section, depending on the direction, is different. So if it's propagating in the X direction, so the same direction as that the train is traveling up, is actually the lowest noise out of all the different directions. The highest noise propagation is the PX, which is behind the train. So that's important to know. And then the other noise is coming from there, different depending on the direction of that you are compared to the train, and they range between 102.3 to 107.6 decibel A's. Okay, so that's the end of this podcast. I'm going to finish off this paper, which looks at a lot of different flow structures and pressure coming off of the pantograph in the next podcast. And we're going to look at how the LBM CFD fares. It's going to be interesting, so I'll see you in that podcast. And if you want to get better at CFD, so we've been talking about LBM here, but if you want to get better at CFD in general, so we have other courses from beginners to advanced, check the link in the description. We have courses there. And if you want to make your experiments more accurate, including your validation data, look at the Atmosphere Hawk and get one for your experiments, because that accurately measures the density of air, which changes every day by 2 to 4%. It changes more between seasons and weeks. So what this means is that even the velocity of your wind tunnel will be different because the density is changing. And if you're not accurately measuring the density, then the wind tunnel velocity that you have is not what you think it is. So if you're doing CFD, for example, you then do your CFD and you specify, okay, the density is 1.2 kilograms per meter cubed, the velocity is 20 meters per second maybe, but that's not going to measure, that's going to match your experiments because the experiments are not going to be 1.2 kilograms per meter cubed or 20 meters per second. They're going to be different. So the atmosphere hawk gets rid of that error for you, which makes your validation much easier and takes out those headaches for you. So then your research is much more accurate. So link in the description for that. And we'll see you in the next podcast. Peace out, amigos.